Hello and welcome back to PC Retro Programmer. In this video we're going to be taking a look at how to debug a program that you've written that isn't working the way that you expected. Now of course one way to do this is to add some debug statements to your program. So in other words, print some stuff on the screen or even write a log file which you periodically update with information about what's going on, register values or even just where it's up to so you can see where things stopped working. But we're going to do it a different way today. I've got DOS 6.22 on this machine and we're going to use its debugger. So a debugger is just a small program for running your program and having a look at what's going on while it's executing. So the DOS debugger is debug.exe and you can see it's very, very small in DOS 6.22. It's only about 15 kilobytes. And the program that we're going to debug with this today is one that we wrote for the channel. It is line.exe, and you can see that this is a very small program of only 682 bytes, and all this does is draw a line on the screen, wait for a key to be pressed, and then exit to DOS. So this is an exe file, and debug.exe can handle exe files or com files. They basically work exactly the same way. All the commands are the same in debug, but they will load a little bit differently. DOS loads exe and com files slightly differently, so just be aware of that. So to load a program up, you just do debug and then the name of the program and it'll load it. Now it doesn't actually start running your program straight away. It sits there waiting for you to give it a command, and it's at the moment just loaded the program off disk just the way that DOS does, ready to be executed. Now in order to get an idea of what debug can do for us, we can issue the question mark command, and that's just a help screen and it shows all the commands that are available. There's not very many there. It's a very simple debugger. There are more complicated ones. For example, you can use the one that comes with the Boolean programming languages, the Turbo Debugger. It's a bit more sophisticated, and then there are even more sophisticated ones again. But this one has the advantage of being very, very simple to learn and to use. So each command is just a single letter, as you can see, and there might be some operands as well. Some of these are optional, so those are in square brackets, the optional ones. I won't go through all of these because there's too much for one video. I certainly won't touch the expanded memory ones at the bottom because I don't have expanded memory on my machine. And I'm only going to go through a few of these commands, the ones that are really important to get started with debugging. So the first thing we want to do is to orient ourselves, and the way we can do that is to issue the R command, the register command, with no arguments, and what that does is show all of the values inside the CPU registers. So you can see that these are all 16-bit registers because they're all 4 hexadecimal digits each. That's why we use hexadecimal. It works out exactly right that way. And the first line here are all the general purpose registers in the CPU. So most of those are set to 0 by debug when you start up. The only exceptions are SP here, which is at 100 hexadecimal. That's the size of the stack, actually, 256 bytes. And it always starts at the end of the stack and works down as you put stuff on the stack, so that's why it's at the highest value, 100. And the other register that's not 0 is the CX register, and this actually contains the number of bytes in our program. Now, the program on disk was 682 bytes, and AA in hexadecimal is only 170. But it's only showing you the size of the program itself, not the size of the program on disk. That includes a extra DOS header. And so really all we've got is what's left after the program's loaded from the disk. And so the next line has all of the segment registers in the CPU. So DS and ES for data segment and extra segment. Those just get set to whatever DOS sets them to, so 1759 when the program loaded in this case. And the code segment, CS, is a little bit further along, that's 1769. And the stack segment, which is where the stack is at the end of our program, so 1774. So our code is in the code segment, the 1769, and we'd actually have to set DS and ES ourselves if we were going to use a data segment or an extra segment. Now the next register there is not one that we play around with ourselves. It's an internal one for the CPU. It's the instruction pointer, and that's actually just where the CPU is up to in its execution of your program. So at the moment that's set to 81 hexadecimal, and you might wonder why that's not 0. Surely this is the start of the program. But if you actually have a look at the assembly language file for this program before we assembled it, we actually had something before the start of our program, namely a big function, the function for drawing the line on the screen. And so the actual start of the program itself, the main program, wasn't until after that. And so that's translated to offset 81 hexadecimal inside the code segment. So if we went to offset 0, we'd see the actual line function, which is at that address. So on the right, you can see there are some pairs of letters, and those are actually the flags in the flag register. Most important, of course, is the carry flag, and that's over on the right there. That's at NC, no carry. In the middle, you've got the 0 flag, which is the next most important. That's non-zero. And to its left, the sign, which is currently plus. So the other registers, PO at the end there, that's the parity, which is odd. The next one to the left is auxiliary carry, so that's no auxiliary carry. And then there's, on the left-hand side there, we've got NV. That is for the overflow flag, and that's no overflow at the moment. The next one along is the direction flag, so that's currently up. The other option will be down, of course, DN. And then you have the interrupt flag, and that's currently enabled. The other option would be disabled, of course, but then the interrupts would be off. So on the next line we have the current address of the code that's being executed. So at this moment it's the start of our program, so just CS and IP. And then we have the 2 bytes of machine code for that first instruction in our program, 32E4. Now the debug program is actually translating that for us back into assembly language. Now it might not be exactly what we had in our assembly language program because it's only got the machine code bytes to go by, and sometimes there are even different assembly language instructions that code for the same machine code bytes. They do exactly the same thing, so as far as the CPU is concerned, they're the same. And so debug will just show you one of those, and it may not be what you originally had in your assembly language program. Now it's important to know that the debug.exe program only supports assembly language for the 8086, 8088. It doesn't support any later CPUs, or at least won't support the instructions that are only available on those. So if you have machine code that corresponds to instructions on a 286 or higher, it won't be able to unassemble those properly for you. So you'll need to use a different debugger. But this will be fine for our program because we wrote it for the 8086, 8088. So the first thing we'll do is unassemble our program, and if we just use the U command, it will start unassembling our program from the start address there, 81 hexadecimal. And this is not all of it because we know our program is AA bytes long. That was what was in the CX register when we started. And so it should finish on byte A9. Remember, it starts on 0, not on 1. So A9 will be the final byte of our program. So we can actually unassemble all the way through to A9. And where will we start here? We have to start at the next assembly language instruction. I think that'll be at A2. And the reason I say that is because there were 2 bytes in the machine code at A0. So the next one should be A2, that's correct. And we'll go all the way through to the end of our program, which is A9. And so there's the rest of it. So that's the whole main program unassembled. The other thing we could unassemble would be the line drawing function, which we know is at offset 0. So let's put that in. Now we don't actually need all those zeros, we can just put a single 0 as it turns out. So there we have it, that's the start of our line drawing function. And if I just keep doing U, it'll just keep going from there. So we'd eventually get back around to the start of our main program. Alright, so the next thing we want to do is to start stepping through our program one instruction at a time and actually executing it one instruction at a time to see what happens. And remember, the very first thing our program does is to set the CGA graphics mode. And so this is function 00 of the BIOS video interrupt. So we put 0 into AH. So the first instruction in our program was to XOR the AH register with itself. So that was the first instruction at that address 81. So let's run this, and the way we do that is using the proceed command. So it'll put 0 into AH, and the next instruction is to put 4, the BIOS mode, the CGA graphics mode, into AL. That's the lower half of the AX register. So you can see now there's a 4 in AL, and the next thing we can do is call the interrupt, the BIOS video interrupt, 10H, and take a look at what happens when we do that. So now we're actually in BIOS mode 4, so the CGA graphics mode. It can still print text in this mode because it has a font for that, but you can see it's much larger and it's really a little bit harder to read what's going on here. But we can still cope, Debug can still cope in CGA graphics mode. So the next thing the program does is it starts pushing values onto the stack for the call to the line drawing function. These are the arguments for our line drawing function. So we push on a 2, which is the color, and then we push on 64 in hexadecimal, which is 100, and then we push on C8, which is 200. So remember, we're going to draw to the coordinate 200, 100, and then we put in the start coordinates, which are 0 and 0, so we push 0 twice. And here we're calling our line drawing function, and remember that the line drawing function is at offset 0, 0, 0, 0, so that's what is going on here. There are no labels here, it's just offsets. So when I do P now, it will draw the line, so let's see that happen. And as you can see, it drew it, and then of course the terminal scrolled everything up, so I didn't see all of it anymore. But now the line is drawn and our function is returned, and we're back to the next instruction, which is to clean up the stack. Then we want to wait for a key press, and so that's function number 0 of BIOS interrupt 16 in hexadecimal. So look, it's just sitting there waiting for me to press a key. So if I press a key, it returns. Now it's actually put the key press value into the AX register there, and so we could actually figure out what key I pressed just from that return value. So now the next thing is to go back into the text mode, which is mode 3. So function number 0, XOR AH with AH, mode 3, and call the BIOS video interrupt 10H, and now we're back in text mode. And finally, we exit to DOS. So that's function 4C of the DOS interrupt. Now, what do you think will happen here? Do you think we'll end up back on the DOS command line, or will it be smart enough to know that the program is finished? Let's run it and find out. And it says program terminated normally. So debug knows that we've terminated the program. So that's a quick run through of the program using the proceed command. And we just stepped all the way through, but you'll notice that we didn't see any of the code in the line drawing function itself. It just executed that and then returned back to the main program and kept going. It didn't actually show us the instructions inside the line drawing function one at a time. So how do we get those to show one at a time? Now, to see how that works, let's quit debug and let's just the Q command, and let's run it again on line.exe, and we'll do exactly what we did last time. We will just step through it one instruction at a time, and we'll go up to the point where it's about to call the line drawing code. So it's just pushing stuff onto the stack, and now here it is. So instead of pressing P this time, I'm going to press T for trace, and that will trace into the line drawing function. So here we go, here's the first instruction in the line drawing function. And I can also trace through this, or I can proceed through this. It doesn't really matter whether I use T or P. T will do less than P will do, though, in some cases. So let's see what happens. So it's going to first of all set up the CGA segment. So now ES is B800, which is where the CGA memory is. Now it's going to set up the offsets for the first point on the line. It takes a while to do that, and then it will set up all of the registers ready for drawing the first point eventually, and we'll recognize the pixel drawing code. There's the first instruction of the pixel drawing code executed. It loads the byte from CGA memory into AL, and then we AND and OR, which is the usual thing you do to update a pixel, and then we store it back in the video memory. So that first pixel is now drawn. We don't see it on the screen because it already scrolled right back off again, but we'll keep going. And now here is the if statement that's inside our main loop in the line drawing code, and in fact it looks like the jump was actually taken, so the body of the if statement was not executed. And so now we update our x coordinate, and finally we're at the bottom of the main loop. So the main loop just draws one pixel per iteration. So if I press T again here, what will happen is it will go back to the start of the loop, because we still have lots of pixels to draw. So let's actually do that. So here we are, we're back at the start of the loop again. It's drawing the next pixel, so it gets that pixel from video memory, or the byte rather, and ANDs and ORs, writes it back to video memory, and again it's going to scroll right off the screen. We won't see it, but it's now drawn the second pixel, and this time it looks like the branch is not taken, so we actually get to execute the body of the if statement, and then we're back around to updating the x coordinate, and finally down to the bottom of the loop again. Now, instead of doing T again, which would just take us around the loop again, I'll just do P instead, and we'll see what the difference is. And there you see it drew the whole line. So what happened this time is it just kept on looping until it finally finished all of the iterations, until it got onto the instruction after the loop. And so now we're just basically cleaning up to go back to our main program, and there's the return instruction which takes us back to our main program. So that's a way to step through the line drawing function. So now we're back in code that we're familiar with. We're going to wait for a key press, and we're going to go back to mode 3, the text mode. Now if I press T here, what would happen is it would actually trace into the interrupt handler for the video mode, the interrupt 10H interrupt handler. Now you probably don't want to do that because there's a huge amount of code in there, and you'll get lost in there pretty quickly. So it's always better to actually do P here unless you really want to see how that works. And as you can see, it's changed the video mode back to the text mode, and then we finally terminate the program as usual. And again, if I did T here instead of P, it would actually trace into the DOS interrupt handler. Again, not something we actually want to do, but you can do it if you want to. So that's the difference between T and P. T will trace into stuff, and it will also do everything one instruction at a time. Even when there's long loops, it will just keep going through all the iterations of the loop. P will allow you to shortcut all of that stuff, so it'll shortcut function calls, interrupts, and loops. And so that's the difference between P for proceed and T for trace. Now there's one more command for going through your program which you're not going to be able to do without, and it's the G command. So this stands for go, and what it does is it starts running your program from whatever point you happen to be up to, and it won't stop until it reaches what's known as a breakpoint. So it'll run it through at full speed until it reaches a breakpoint, or of course if it reaches the end of your program. So let's just run it without any extra arguments and see what happens. So you can see it just runs the program through normally and finally terminates the program. Now that's not very useful on its own, but let's see what happens if we add some addresses. So these are called breakpoints. I'm going to add 00A6 because I happen to know that this is the address of the very final instruction in the program, the final DOS interrupt for terminating the program. So let's run it again like this, and as you can see it's stopped at that exact instruction. And so now I can step through the program one instruction at a time. Well, of course there's only one left, so that's also a little bit boring. But you can also tell it where to start from. So let's do line.exe again, and this time we'll do G equals 0081. So that makes it a start address if you put that equals in, and we'll also stop at the OA6 address that we just stopped at previously, and I'll also add another one in. I'll add address 0. You can put as many addresses as you want, as many breakpoints as you want. Now 0 is the start of our line drawing function. So this time it's going to run the program through until it either gets to OA6 or until it gets to that line drawing function, whichever comes first. So, and it's going to start running at 0081, which just happens to be the very start of our program in this particular case. Alright, so there you go. You can see that it stopped at the very start of the line drawing function, and now we could just proceed through one instruction at a time, just as normal from that point on. And of course if we want to go through to the end of the program again, we just put the OA6 and there we go, and we could even step through from there. So this is a great way of running bits of code at full speed and then stopping immediately afterwards so that you can trace through one instruction at a time from there. Now there's a few times that you might want to do this. For example, there might be some time sensitive code which really needs to run at full speed, otherwise the debugger would screw it up, and so that can be useful if you want to run that through and then keep going. Another problem that might occur is you might end up in a graphics mode, which makes it so that you can't read the output of the debugger. It might be some really weird screwy graphics mode, and so you want to run that portion of the program through and then keep going with your single stepping after that. So you just find an address that is in your program after that piece of code's run, and you just pass that to the G command. So there are lots of other reasons, there are lots of other things that can screw up debug, and so this can be one way of getting debug to work in cases where it otherwise wouldn't. But it also might just be that you don't have the time to go through all of those instructions one by one, and you know what they all do and you know they're all working. Maybe you already looked at them in a previous debug session. You just write down the address of where you got up to in the last debug session that you did, and the next time you can basically go straight there. It'll just run all the way through to that point and let you keep going. So there are lots of different reasons this is useful. It's a very, very useful and powerful command. But there's one other way to use this. So let me open up the original assembly language for this program. And what we're going to do is we're going to add our own breakpoints this time. So the way it's done is just to call interrupt3, and this is the interrupt that the debugger uses to stop. So let's save our code, assemble it again, and link it, of course, to get a new executable. And now we'll debug again. At this time, when we issue the go command, it will stop at that interrupt3, and there it is. So that's also very handy. Sometimes you don't want to spend the time of figuring out within debug exactly where you want to put your breakpoints. It would just mean unassembling lots and lots of code, and it might take you hours to do, but you might be able to pinpoint the exact location where you want to stop in your source code really easily. And so it's also useful when debugging higher level language programs, by the way. If you have the ability to add breakpoints in those, then you can really save yourself a lot of time by putting one exactly where you want to stop, the exact point where you think things are going wrong and you want to trace through step by step. So very handy. Now there's one slight annoyance with this. If I now do P, it will just keep stopping here because this particular instruction is designed to stop the debugger, and of course it's not going to proceed. So T won't work here either. What that'll do is trace into the interrupt handler for interrupt3, and that's almost certainly not what you want to do. So you have to actually tell it to start from the next instruction, and the way you do that is again with an equals. So P equals 0040, which will be the next address after the int3, and then you can keep going from there. So that is a little bit of an annoyance, and basically if I want to go through to the end of the program now, I should be able to just with a G. So that's the go command. And the next command that I want to show you is one for modifying a program while it's loaded into debug. So first of all, let's just remind ourselves how our program works. So we'll unassemble here, and you can see that at offset 0083 we have an interrupt 10. Now this is the one for setting the CGA graphics mode. And further down at offset 0094, you can see there's a call 0000. So that's the call to our line drawing function. And the code in between is actually setting the color of the line and the coordinates of the line. So why don't we change the color of the line? Let's suppose we've done a debug session and everything worked fine with color 2, and we want to change it to color 1. So that means we'd have to modify the line of assembly at offset 0085 there. So it currently says move AL02, and we want to change it to move AL01. So the way we do that is using the assemble command, which is an A. So I put in the address 0085, and it brings me up a little prompt, and now I just type in the assembly that I want to be at that location. So move AL1 this time. Now I could actually just keep going here and putting more assembly instructions in. Bear in mind that the machine code for each instruction is not the same length. So obviously there's some limitations on what you can actually do here. If you put in an instruction that has a longer length than what was there, then it might overwrite the next instruction. And if you put in an instruction with a shorter length than what was there, then there's some extra bytes that are going to be left over. You can replace extra bytes, by the way, with NOP, N-O-P, and this will just do a 1 byte instruction that does nothing. So that's not such a big problem, but putting longer instructions in is probably going to screw things up. At any rate, once you're done and you put all the instructions in that you want, you just press enter again. And let's take another look at this same piece of code. I have to give it an address, otherwise it'll just keep unassembling from where we finished last time. So let's put OS7F in again and display the same piece of code. And now you can see I have at offset 0085 move AL01 instead. So basically now I can run my code with this change. So let's do G and it'll just run the whole thing through. And now you can see that I have a blue line instead of, or cyan really, instead of magenta. So this is a really great way of changing what the program's doing essentially while it's running. Now there's one more command that I want to show you, and this is for looking at memory. So let's just bring up our registers, and I'm going to issue the D command, D for dump, and we'll see what happens. So it looks like it's dumping bytes of memory, and it's starting at 1769 for the segment, so that's the code segment by the looks of it. If you look at the CS register above, that's 1769. And it looks like it's starting at the far right of that line. That line starts at 0070, so that must be 007F, that very last byte. And 007F is what's in our instruction pointer. So in other words, it's started to dump from CS:IP, and it looks like this will be part of our program. Basically what we're looking at here is the machine code for our program. Now this is not very interesting, but we can also dump the data segment. So let's do that. So DS:0000, and now it's dumping the data segment. You can see the segment address it's using now is 1759, which was in DS. And if I just keep dumping here, we'll also see some strings on the right hand side. So those bytes that are in the data segment there actually code for an ASCII string. And so each of those bytes is an ASCII code for a letter. So this is a great way of looking at strings in memory as well. So of course we can also give it a full address. We can actually look at the very beginning of memory if we want. This is the interrupt vector table at the very beginning of memory, and we can just have a look through that. And so you can see that this is a great way of checking out what's going on inside the memory of the machine, and if there are any strings there, you'll be able to see them on the right hand side. So that's all I really want to go through today. I've added a link in the description to a really great website on MS Debug. It has a lot more information than I gave today, including information about all the commands that I didn't cover. And so check that out if you want to get to know how to use this really useful program in much more detail.